All right, everybody. Thank you all for being here today. This is the March 2015 webinar from Staties Incorporated. My name is Martin Beziner. I'm a statistician here at Staties. We are located in Minneapolis, Minnesota, in the United States. Today's topic will be practical strategies for model verification. Okay, today we actually have a small crowd, but anyways, to avoid any disruptions, everyone will be muted. If you have any questions during the talk, feel free to ask them in the chat feature of GoToWebinar. My colleague Brooks Henderson is with me tonight, and he'll be answering the questions as they come in. If later, after the webinar or sometime tomorrow, a question occurs to you that you maybe forgot to ask during the webinar, you can feel free to email us at stathelp@staties.com, and we'll try to answer those questions as soon as possible. And as one final note, this presentation is already posted at www.staties.com/webinar.html. So later on, you can go ahead and get a copy for yourself. And also within a week or so, a voice-over PowerPoint should also be available at that website. Before we get into the material, if everybody that hears me can just click the raise hand button, I would appreciate that very much, just to make sure that there aren't any issues with the sound. Okay, so I do see that several people have raised their hands, so as far as I can see, we should be all set to get started with this event. Okay, so some introductory comments. First of all, model confirmation is an important step in any industrial experiment. In fact, it's a crucial step in many cases. As consultants, and having worked with many people in industry, we've noticed that this step usually receives very little attention, if any attention. Sometimes it's completely ignored, which is not a good thing. Ignoring this step can result in statistical models that really perform poorly when they are used in the future. If you are working in a situation that involves predictive modeling, in other words, building models that will be used to predict future events or future outcomes for example, that may not have been taken into account during the experiment, you'll want to confirm your model. So the summary, so to speak, is that model confirmation will give the experimenter confidence that statistical results can be used in future applications. Today's webinar will be divided into 3 parts. The first part has to deal with this issue of model checking versus model confirmation. Most people that have taken an introductory course in statistics or in experimentation will probably already have dealt with this issue, or will have at least heard of this issue of model checking. We'll also define what is model confirmation, how is it different than model checking, and why the difference is important. In part 2 of the talk, we'll actually go ahead and give you some approaches that you can use if you ever do go ahead and decide to use model confirmation in your future work. There will be 2 major examples that are presented. One is fairly straightforward. One is a fairly straightforward response surface industrial experiment. Another one, the second example, is more relevant to pharmaceuticals. So we do have a nice variety of cases. And we'll conclude this talk with some practical tips and tricks. Lots of wisdom that we've collected from many sources over the years that should hopefully help you when you go forward with this in the future. So why don't we go ahead and begin by talking about model checking versus model confirmation. Okay, so we'll begin with kind of a short, motivating example. So for the experimenters that are here with us, you may find this chart to be familiar, because in a typical industrial experiment, there are usually these 5 steps. First, there's a problem that needs to be solved. So your job as an experimenter may be to actually formulate that problem clearly and determine the goals. Okay, and when we say determine goals, usually the goals try to be numerical goals. For example, saying something like, we want to improve our process, we want to improve the drug, are usually not quite as informative as saying something like, we want to maximize a response. We want to reduce the time it takes to run the process by 10%. We want to increase the results by 3%, and so on. Afterwards comes a planning stage. When you experiment, you should always spend a lot of time carefully designing your experiment. This can be done in a number of ways. For example, if your design is fairly straightforward, there are lots of textbook designs, as we like to call them, that may help you, that may be relevant to your problem. If you have a slightly more complicated problem, which is almost always the case, as we've seen, you'll want to use software to design the experiment. For example, the Design Expert 9 software is one potential tool. Afterwards comes the most lengthy and most expensive part of this entire sequence, which is actually performing the experiment. Finally, after you've collected your data, you'll usually build a model. Again, this is almost always done using statistical software, such as Design Expert. And the last step should be to check the model assumptions. In other words, did the tool you used to analyze the data do an adequate job? Was it the correct tool? I'm going to begin by giving an example, an industrial example that's fairly straightforward, but it'll really help us understand the issues of model confirmation in a few more slides. So here's the situation that we're going to start with. An engineer is interested in studying a chemical reaction. In particular, he's interested in 3 factors that he can vary. For example, time. So the low level of interest would be 40 minutes, and the high level of interest would be 50 minutes. He can also vary the temperature. The lowest level of that he's interested in is 80 degrees Celsius, and the highest is 90 degrees. Finally, he can also vary the catalyst with the range from 2% to 3%. The engineer measures 2 responses during the experiment, one of which is conversion or yield in this case, and the actual activity. I have conversion highlighted in bold because that's really the response that we're going to work with. And if the engineer understands the underlying process, in other words, how does time, temperature, catalyst interact and affect the conversion, that'll give them a better idea of how to control the chemical process, which can potentially lead to reduced waste and increased profits. So these are definitely desirable properties, and model confirmation will play a big role in achieving these goals. The design will be run. The engineer uses a central composite design, which consists of 6 center points, which are here in green. Okay. Let me go ahead and actually circle these points as I describe them. So here are the center points, and there are 6 of them, which are run at the midpoint of the 3 factors. So those are run at a time of 45 minutes, a temperature of 85, and a catalyst of 2.5. Then we have 8 factorial points, which are the points here on the corners of the cube, and these points are run at triplets of these values here. So for example, 40, 90, and 2 would be a point here on this cube. And finally, there are these red points which actually extend outside of this edge of this cube, which are called the star or axial points, and help determine if there's curvature, and also to give some information about the process outside of the design space. I'm not going to go into more detail about this because we really care most about the end results, but any standard textbook or introductory course on design of experiments will surely mention the central composite design. And one final note is that 12 of the runs out of the 20 were performed using one machine, and 8 of the runs were performed using a second machine. So there are 2 blocks. And this will be important later when we talk about confirming a model in the presence of blocks. Okay, we use the Design Expert 9 software to actually analyze these 20 runs. Here to the right, you can see is basically the output. This is basically an analysis of variance. And we choose to fit a quadratic model to the data. Okay, so as you can see here, we have linear effects of time, temperature, and catalyst. We have the two-way interactions. And we also have the quadratic effects of time, temperature, and catalyst in the model. Now you might be saying, well, wait, the p-value here, is 0.3790, corresponding to time. You might say, well, that's not small, but we actually do include it in the model because of the fact that this AC interaction is very small. So whenever we have terms that incorporate another term, we'll include all of the individual terms. So because A and C is in our final model, we'll also include A and C, no matter what their p-values are, to maintain model hierarchy. Okay, so this is a fairly straightforward analysis of variance. And this is probably a tool that you may have seen. It's a very common tool for analyzing this type of data. Okay. You have your important effects in the model. You'll have model coefficients so that you can actually estimate how does time affect conversion, how does temperature affect conversion in catalyst, and so on. But you may now be asking yourself, well, how do I know that what the work I've done is actually good? How do I know? I mean, I may have just crunched these numbers by following some textbook, but I don't know if this applies to my particular problem. Well, the first thing you may do is you may look at this row here that says lack of fit. Okay? And you may see that the p-value of 0.8574 indicates that there's not really much evidence. There's no evidence that a quadratic fit is inadequate. So a quadratic fit in this case looks to be okay. However, as I mentioned a few slides back, every statistical tool is kind of tailored for a specific problem. And most tools, such as the analysis of variance, come with a set of assumptions that need to be satisfied so that we can actually go ahead and trust these p-values, for example. What are the assumptions that we would need to check with the analysis of variance? Again, we'll just talk about these quickly. We would need the residuals, which is essentially the difference between the predicted value from the model and the actual value. We would need all of those residuals to be normally distributed. In other words, if I took all of the differences between the observed data and the responses that were predicted with my model, and if I made a histogram of them, I would expect to see the histogram to be approximately bell-shaped. Okay, not skewed, not uniformly distributed, but I would want there to be a nice bell pattern where most of the residuals are in the center and close to zero. Also, I want my residual variance to be constant. What that means is that the model predicts with the same accuracy across the entire design space. What I don't want to see is, for example, the residuals or the error to increase as the response increases, which actually is quite common in practice, but I don't want to see that. the tool I use to analyze this data requires that throughout the entire design space, my model can measure with approximately equal precision. And finally, the analysis of variance assumes that the residuals are independent across the run. So I don't want to see any drifts. I don't want to see, I don't want there to be a case where, for example, the residual at run 5 gives me information about the residual at run 2, and so on. So using Design Expert 9, I'm going to go ahead and quickly check these assumptions. I want to check to see if the assumptions of the analysis of variance were satisfied. I'm only going to go through a couple of these plots, just the most important ones. And the first one, the first plot that I have here is what's called a QQ norm plot. And this plot tests to see if my residuals are approximately normally distributed. What I want to see is most of the points falling along this line. There may be an exception or two, which is fine, but if I took a very fat marker or pencil, I'd want to be, and if I placed it over this red line, I'd want to see almost all of the points covered up. In this case, we don't see any major issues. To check the residual variance, remember, we want the variance of the residuals to be constant. Otherwise, the tool that we chose, the analysis of variance, may not have been appropriate. We may need some fixes. What we want to see here is we want to see, in this plot, the residuals versus predicted plot, we want to see random scatter. What we don't want to see is like a triangle or what we call a megaphone shape, which would indicate that as the response increases, so does the variability around the predicted response, which could happen because sometimes when a process naturally produces a higher output, that output may be more difficult to measure and you might get a less precise measurement. However, here we actually see that this plot looks pretty good because we see random scatter, we don't see any obvious patterns. And finally, we want to check the residual autocorrelation. In other words, we want to see are the residuals independent, and to do that, we'll take a look at the residuals by the run. Okay, and what we'll see here is that there aren't any clear patterns in this plot, which indicates that everything looks okay. Another thing that we would want to do, of course, this is something you should always do, is to actually check the model accuracy by plotting the fit, which in this case is this nice green surface that was generated using Design Expert. And you want to also take a look at the points. Here we see that this curve appears to nicely fit these red points, which are actually the observed data points. We don't see any of these points way above or way below the curve. And similarly, we'll also want to go ahead and check the center points. Now, I do apologize. I didn't realize that this plot didn't look all that great until just recently. So in order to check the accuracy at the center points, what I'm going to do is I'm going to actually just look at the one-factor plot. And I'm going to see, are the center points approximately, are the center points being predicted well by my model, by my fit? And in this case, it looks like we're okay, because on average, we've got some points above, we've got some points below. But this is something you always want to do. You always want to graphically take a look at your results. You want to see what's going on. This is an obvious way that you can detect issues without even having to do any complicated procedure. Finally, the last kind of visual inspection, because these are all really visual tools, there's no number you're getting here, there's no p-value. The last thing you can check that might be very useful is an actual plot of the predicted values versus the actual values. Now, if your model predicts well, if you have a good model, a model that fits well, what would happen is that most of these points would line up close to this line. Okay? Now, some people will say, well, we want all of the points to be on the line, which is not necessarily a good thing to say, and we'll talk about why in the next slide. But here it looks like looking at this intuitively, kind of doing a quick visual inspection, we don't really see many issues here. We see that most of the points are close. We don't see any huge outliers. We don't see any indication that maybe we should have had a linear model instead of a quadratic model. So everything looks good. But here we're going to now talk a little bit about model checking versus confirmation. What we did is we checked to see if the tools that we used, which in this case was the ANOVA, if that tool was appropriate for the data set that we had. However, this is something that you probably have learned in a basic statistics class. But why is this not enough? Why should you do more? Why should you confirm your model? Well, first of all, if this engineer goes and repeats this entire experiment, let's say in the next year, the model that I just fit a few minutes ago will probably not fit that new data as well as it fits this current data. That's because this current data has some particular features, some particular small irregularities that may not appear in the next execution of this experiment. So when you're assessing the goodness of a fit of a model using only data that you used to build the model, what'll happen a lot of times is that you'll get over-optimistic results. You'll get a plot like this one here where, yes, the model fits this data well, but how do I know that if I replicate this experiment in the future, or if my colleague replicates this experiment, or some other company replicates this experiment, how do I know that this predicted versus actual relationship will still be this good? Okay? So what we just did doesn't really tell you much about that. Also, if you just use what we used to assess the predictive accuracy, meaning how well will this model predict in the future, your results are generally going to be too optimistic. The results are going to be way too good. You will be disappointed in the future. It is much easier to describe a data set that you collected than it is to actually fit a model and predict observations that you have not even seen. Much tougher problem, which is really the focus of this talk, this webinar. So model confirmation uses new data, fresh data that was not used to actually build the model in order to assess the model adequacy. Okay? Model confirmation, what it does is it gives the experimenter an idea of how well a model will predict future cases. So if I go back to my design space here, okay, I observe data at these points, but let's say, for example, I want to predict the response here, okay, or I want to predict a future response at this axial point. In order to get some idea of how well this model will do, I need to use confirmation. I need fresh data, unbiased data that was not already incorporated in this model. So, hopefully, you will check your model assumptions after actually analyzing and building the model. This tells you if, mostly, for example, the p-values that are reported are valid. Okay, but hopefully you'll go and do one additional step, which is to confirm or verify the model. Okay, so let's continue with this. Let's go ahead and continue with this example. So just for convenience, I put the output, put the ANOVA here on the right side of the screen. And let's say, for example, that the experimenter wants to maximize conversion. Let's say that that'll lead to increased profits. That'll lead to a better chemical reaction. So we'll go ahead and use Design Expert 9. This is a particular goal. We'll go ahead and use Design Expert 9 to find the combinations of time, temperature, and catalyst that actually will maximize conversion. And we'll go ahead and just search, just for simplicity. This isn't necessarily the best way to do it, but for simplicity, we'll just go ahead and search over the cube. meaning time will be between 40 and 50, temperature will be between 80 and 90, and catalyst will be between 2 and 3. We won't go beyond the edge of the design space just for simplicity. This in itself could be the topic of an entire talk, but it's not the topic of this talk. Design Expert 9 tells me that the maximum conversion occurs actually at the corner of the design space. It occurs when I set the time to 50 minutes, a temperature of 90 degrees Celsius, and a catalyst of 3%. In fact, you can get this nice contour plot here, which will actually show the conversion as a function of time and temperature when the catalyst is set to 3. Well, why do I set the catalyst to 3? Well, the reason is I can't actually draw another axis here. So I see that as time gets larger, okay, and as temperature gets larger or smaller here, it looks like I get a better conversion. Now the question is how do I know that this solution is valid? If I repeat this experiment tomorrow, how do I know I won't get, for example, a time of 45, a temperature of 85, and a catalyst of 2.7? Okay, well, I'm going to go ahead and use model confirmation to give me extra evidence that my optimal solution, that the response is actually maximized at this corner right here. Okay, so this brings me to the second part of this talk, which is actually some approaches to confirmation. I'm going to talk about two approaches that are fairly straightforward, and I'm going to introduce a third approach that you may not have seen before that can be quite useful in cases where you can't do these two steps. Okay, so the first approach, well, first slide is really kind of a not very exciting slide because it's actually no confirmation. You could always choose to not confirm a model and then take the results as they are. Is this ever a reasonable thing to do? Well, in some cases, it may be the only thing you can do. So, for example, if the experimenter believes that the model is valid using scientific knowledge, using previous results, and so on, and if the result of the model not being valid isn't catastrophic, it may make more sense to not go forth with the confirmation. This is usually a rare occurrence, okay, and typically only occurs when your work involves a non-critical process. In some cases, you may have no choice. Okay, you've used up your entire budget for the experiment and you just can't afford to obtain any additional runs to confirm the model. It also may not be physically possible to run further experiments because you've destroyed, the experiment that you've ran consumed all your raw materials and so on. Another case where actually where you can make an argument that model confirmation is not very necessary would be if you're doing a screening design. In a screening design, you're only looking to identify a few large effects, and those results will help you when you go forward. Okay, so if you can't confirm a model from a screening design, chances are the results won't be catastrophic, but in general, as statisticians and consultants, we in general do not recommend skipping model confirmation, although we do understand that in some cases you just can't do it, or in maybe in cases like screening you might be able to get away with not doing it. Okay, now I'm going to talk about simple confirmation, which is probably the most common way to confirm results, to confirm your model. One thing you can do, for example, is if you do fit a model and you do use software to obtain a point in the design space that has that looks good for some reason, for example, a point that might maximize the response, might minimize a response, and so on, you may later on go back and at that point perform one experimental run. just one run at those optimal settings. Here are some comments about that. For example, if the experimenter believes that the model is valid, then maybe one run might be enough. Being wrong is unacceptable. If the budget or time is really tight, then you might only want one observation. Again, one observation is much, much better than no additional observations, no additional confirmation runs. Also, if the design doesn't have blocks, or if the block effects are fairly small, maybe one observation, one confirmation run might be acceptable. Okay, so what'll happen is the way to confirm a model in this case is to compute a prediction interval at the optimal settings. Okay, this can be done using software such as Design Expert 9, which provides a very fast and flexible way to perform model confirmation. So just as a wrap-up here, remember, one confirmation run is much, much, much better than no confirmation at all. So let's go ahead and continue with this industrial example here. This is the confirmation node from the Design Expert software. If you look here, you'll see that we're at the optimal settings. We're at the combination of time, temperature, and catalyst that actually maximized conversion. We see what the predicted conversion is here. N equals 1 can be set here, which means that we'll just have one confirmation run, and we'll have a prediction interval that's automatically computed by Design Expert here. For those of you that might not be familiar with the idea of a prediction interval, what this means is that we are 95% confident, okay, or about 95% sure that the next run at these settings will be in this interval here. Okay, so this gives us information about the next run, which corresponds nicely with the idea of only doing one confirmation run. And here, let's say that the confirmation run that the experimenter did after fitting the model was 94.02. He can go ahead and plug it in here. We can go ahead and plug in this response here. It'll appear here. And because 94.02 is in our 95% prediction interval, we don't really have a reason to believe that this model isn't valid going forward. It looks like a fresh run, an independent run that was not used to build the model, agrees with what the model is predicting. So in the future, we would have some evidence. We can be somewhat confident that these results will hold true in future examples. Now, even better, as I mentioned before, one confirmation run is much, much better than no confirmation, but even better would be to have multiple confirmation runs. So in other words, you may have some optimal settings, you may have some minima or maxima that you want to test, you want to confirm those points. Why would you want to use multiple confirmation runs? Well, the experimenter may believe that a model is valid, but the risk of being wrong is unacceptable. There's too much money on the line. There's too much, it's a very important project, and you really need lots of evidence that your model is valid and can be used in the future. In this case, you always want to go ahead and confirm with multiple confirmation runs, if of course that's possible. If whatever organization you're working with prefers data-driven decisions rather than opinions, informed opinion, then you should try to perform multiple confirmation runs. Obviously, the budget and time has to allow for multiple confirmation runs. This is kind of a given. Finally, if you fit a model that has blocks, you'll definitely want to at least try to get a couple of confirmation runs so you can run them at different blocks and have those effects cancel out. So how would we confirm the model? By using N observations? Well, again, we would compute a prediction interval, and we would see if the average of the N confirmation runs is in that prediction interval. Again, I'm going to go ahead and use Design Expert 9 because we do feel that model confirmation is important, we do have this convenient node here. Once again, we are at the factor levels that maximize the response. Okay, and we're actually going to go ahead and do 4 confirmation runs now. I'm going to go ahead and enter them here in this little data entry tool. And when I take the average of these 4 responses, I get 88.68. Notice here that I actually did, remember in this design, you may not remember this, but in this design I had 2 blocks because I had 2 machines. So just so that I can get the machine effect to kind of cancel out, I'm going to perform 2 confirmation runs at the first machine and then 2 confirmation runs at the second machine. And what I end up getting is a mean of 88.68. Bad news. Okay, you might be saying this is terrible because 88.68 is actually outside of the prediction interval. The question is then, what should we do? So this slide will give some tips on what to do if there actually are problems. What happens if the confirmation runs don't agree with what the model is predicting? First of all, you may have overfit the model. Okay, what happens when you overfit the model is it's too specific to this particular date, to a particular data set, and when you have a data set that's just a little bit different, the predictive performance just falls apart. So you want a model that's general enough that it's not overfitting your particular data set. So one thing might be to try to reduce the model. You also might want to see if a transform is necessary using a tool such as a box-Cox plot. Another thing that might be causing this discrepancy is the fact that you have problematic model points. You might want to check to see if there are any outliers, both in the points you use to build the model, as well as the confirmation runs. One of these points may not be representative of the true underlying relationship between the factors and the response and may cause a discrepancy. So in other words, go back to the actual spreadsheet where you collected the data and just take a look, see if there were maybe any runs that may have been off a little bit. This is also why we suggest sometimes collecting information about the particular run, so later when you go back and diagnose issues, you'll have additional information to help you out. Also, there's also this issue of too much data. Now this usually is not an issue, but if you ever if you ever have a data set that's humongous, meaning thousands and thousands of runs, what's going to happen is that everything will be significant, okay, including all your effects. Tiny model irregularities will also be detected because you have such a large amount of data that basically you measure everything to very high precision. The problem is that even though something may be detected as significant, such as an issue with your model, you don't really care about it. It's not practically relevant. So this is something that you may want to keep in the back of you may want to keep this in the back of your head at some point, in case if you do ever analyze the data, then if you do analyze a data set that's very huge. And with the increased automated experimentation that we've been seeing, this actually could be an issue in the future. Quick statistical detail. How were those prediction intervals computed that we just saw in the previous slides? Well, this is kind of a standard formula. We have the predicted response. We have the error of the we have the error here. And we also have a multiplier that's chosen to achieve a pre-specified confidence level, which in this case would be 95%. The only difference between a prediction interval based off of one confirmation run and a prediction interval based off of many confirmation runs is this n in the denominator here. So you'll see that as you have more confirmation runs, the prediction intervals will be smaller. Okay? Big question. This is a question that we get very frequently. How many confirmation runs Might 1 be enough? Do we need 5? Do we need 10? We'll talk about this briefly now. This is kind of a very intuitive example. It's not super exact, but it's just meant to get across the general idea. Okay, in general, the probability of detecting an issue with your model, if there actually is one, meaning the probability that a confirmation run will not lie in the prediction interval, as it's related to the number of confirmation runs, usually looks something like this. So on the x-axis we have the number of confirmation runs, and on the y-axis we have the probability of detecting an issue. As the number of confirmation runs increases, you'll see that the probability of detecting an issue also increases because we have more precision, we have less variability. And actually, if you let the number of confirmation runs grow, this will actually approach 1. So, again, this is not an exact picture, but this relationship holds true in many, many cases. So here's one thing you can see. Now, I started this point here. Okay, let me go ahead and circle this point. This point here corresponds to 1 confirmation run. Okay, this point here, this next point, corresponds to 2 confirmation runs. So as you may notice something, as I increase the number of confirmation runs, the ability to detect an issue with the model increases, but it increases at a much smaller rate. The biggest gains appear to come from the first few runs. So, what can we get by using this bit of statistical theory? Well, of course, more is generally going to be better. I mean, you can't really argue with that. We generally recommend at the very least 2 confirmation runs at the points you want to confirm. Okay, again, going back to this plot, you'll see that the biggest gain you get is when you add that second confirmation run. So you should it's kind of like you want to go for the low-hanging fruit first, okay, because that's kind of the easiest place to start. Everything else might be a luxury. The best bang for your buck, kind of the balance between the number of runs and the ability to detect issues, is usually around 3 or 4 runs, as we've seen here. Anywhere beyond that will just give smaller incremental improvements. As a warning, you should probably try to avoid excess confirmation runs. If you have the ability to do 100 confirmation runs, it's probably better that you do 95 of those, that you use 95 of those to actually build the model and reserve about 5 for confirmation. In general, those runs would be put to better use as model building runs. Finally, okay, I'm going to kind of finish up this these approaches to confirmation by talking about concurrent confirmation. Concurrent confirmation is used when it's not practical to perform confirmation after you've already done the experiment. Okay? This can occur if, for example, the experiment takes a very long time. For example, experiments involving establishing a drug's expiration date. These are usually very lengthy experiments. We'll see an example shortly. So if you want to confirm a model that you'll have to wait even longer, which sometimes is just not feasible. If the time on the equipment, okay, for the design is expensive or limited, for example, you may not be able to go back, or it might cost you a lot of money to go back. For example, a case that we worked on was wind tunnel experiments. Very expensive to go back later and perform confirmation runs, so it would be nice if we can somehow simultaneously fit and confirm a model. Finally, if you just have one shot at experimentation, you can't go back. So you'll have to somehow incorporate model confirmation during the actual design stage. Okay, so how is this done? How do we do concurrent confirmation? It's called concurrent because it's done at the same time as the actual experiment. Now, these are, here I say, AKA verification runs. kind of loosely interchange verification and confirmation, so bear with me there. What we do is we add verification runs to and randomize them within the model building runs, which we call the DOE runs. So we'll do the confirmation runs and the runs that we use to build and analyze the data simultaneously so that we don't have to go back later. The verification runs that are a part of the design plan are not used to estimate the model. They're held back until the very end. And finally, the predicted values of the verification runs from the model are compared to their actual values. This helps us confirm model predictions and assess the predictive performance of a model on data that was not used to fit the model. So again, it's kind of like an independent check, independent, unbiased check. Here's an example that I found to be quite interesting, and this has to do with drug stability and studying the degradation rate of a drug. So typically, how do we do these studies? How do we assess, for example, the stability of a drug over time under varying conditions? Well, what you'll do is you'll store that drug under many different conditions that test its stability to external factors, for example, moisture, oxygen, temperature, all these different things. Typically, these drug degradation studies take a very long time to complete. You need to actually observe the drug degradation for a significant amount of time before you can actually make claims about its degradation. So this usually takes months to complete, and you generally having to go back later to confirm a model that you fit that involves drug degradation is just not feasible because it takes too long. Why is this important? This is very important in pharmaceutical applications because it helps establish a drug's expiration date without actually needing to observe the drug for years. This can also be used to help establish manufacturing and packaging strategies to ensure that a drug lasts at least as long as its stated expiration date. We'll now go ahead and move on to our second example, which will help kind of combine all these ideas that I talked about in the last 5 slides or so. In this particular example, I have 3 factors that I think are relevant to the drug degradation rate. The first is water activity. We expect that the drug degradation rate will increase linearly with the amount of moisture, with the amount of water activity. We also consider oxygen, and we expect the rate to increase exponentially with increasing oxygen. So if you increase oxygen by a small amount, the rate will actually shoot up quite a bit. It won't follow a linear pattern, so we'll go ahead and view oxygen on the log scale. And finally, temperature. We expect there to be an Arrhenius relationship between the drug degradation rate and temperature, so we'll go ahead and assume that the drug degradation rate is proportional to the inverse temperature. The design that's run is a face-centered design with 15 runs. This is almost identical to the previous design that I showed you way at the beginning, the only difference being that these points here, these 6 points, okay, no longer extend beyond the face of the cube. Okay, in this case they're actually on the face of the cube. Okay, and we have a total of 15 points. So we have 8 on the corners, we have 6 that are in the middle of the edges of the cube, and then 1 in the center. Okay, we want to evaluate 2 things. We want to determine whether this Arrhenius relationship between the drug degradation rate we want to determine whether the Arrhenius relationship between temperature and drug degradation rate is valid. So what we're going to do is we're going to also pick temperatures that are between the high and the low value, and also we'll pick some that extend beyond this edge of the design space. This will help us kind of validate the drug degradation rate. Also, we'll go ahead and incorporate some additional points here in the design space to help us evaluate predictions away from the cube. The reason why we pick these points here, and we don't say pick them on the left-hand side, is because these points here, the degradation is actually faster because water is higher, oxygen is high, and so on. So these are the 8 verification runs. Okay, I'm going to go back here just for a second, that will be run at the same time as this experiment, and everything will be run in a randomized fashion. But these 8 points here will not be used to fit the model. They'll only be used to help us evaluate the validity of the Arrhenius relationship and the ability of the whatever model we fit to predict beyond the original design space. Okay, so this slide is a little technical, and I'll do my best to try to explain it concisely. What we see here is we see that temperature varies from 40 to 70. We see that oxygen varies from takes the levels of 0.2, 2, and 21%. And we see that the water activity is 0.05, 0.20, 0.35, and 0.50. The black dots correspond to those correspond to these circles here in the design space. They are part of the original design and will be used. I'm sorry, the black dots and the green dots are actually the model building points here. The triangles here are the points that help us establish the predictive ability of the model beyond the original design space. And the squares here are used to evaluate the Arrhenius relationship. That is drug degradation actually proportional to the inverse of temperature? Now, remember, what we're doing is measuring a rate. We're not measuring the amount. We have to actually measure a rate. So we need to somehow, when we have our drugs set up under these conditions here, we need to somehow actually see its rate. For example, how much does it degrade each week, or how much does it degrade each day? So what you'll see are these colored boxes here. Is what we end up doing in this, what ends up happening in this experiment is that all of the design points in the blue region, okay, we measure the drug degradation at 2 weeks, 4 weeks, 8 weeks, and 16 weeks. This is done because we expect the drug to degrade slowly in this region. Conversely, once we move up to the yellow region, we expect drug degradation to be quite fast. So we would actually measure the drug 4 times. Okay, we'd measure it at 1 day, 3 days, 1 week, and 2 weeks. And then we would try to look at these 4 time points that each of these points are measured at and actually somehow estimate a degradation rate. So hopefully this is clear. I know I do understand this is a somewhat involved example, but it really illustrates this idea of concurrent confirmation quite nicely. And what we do, once we do observe the degradation rates, once we do observe the degradation at 4 time points at each point in the design space, and each point in the design, is we actually measure a rate. So for example, here in this left plot, we have the drug degradation as a function of time, the number of weeks here, and we actually fit this line here to these 4 points, and what we see here is that approximately 0.1% of the drug will degrade each week. Okay, on the other hand, under water activity of 0.35, temperature of 50, and oxygen of 0.2, we see that the degradation here is much higher. Okay, we see that the slope here is much higher, and we see that approximately 0.35% of the drug will degrade each week under these conditions. These Ks, okay, are actually what the responses will be when we fit the model. So recall, it's the rate of degradation that we're trying to predict, and that can only be done if we observe the degradation over a few time points. So I'm actually going to go ahead now and fill in the data here, fill in some of the data. These red circled values here, which I've already actually circled, are the two degradation rates that we computed, and they correspond to these 8 points along this yellow vertical bar. Remember, right now we're just focused on the Arrhenius relationship, on validating the relationship between temperature and drug degradation rate. So we'll go ahead and fill in the actual responses that will be used in the analysis. We did mention that we were going to look at oxygen on the log scale because that relationship is exponential. And we're going to actually look at the inverse temperature now. However, we will convert it to the Kelvin scale here. Now, what we do is we look at these red Arrhenius verification points, the ones that are trying to measure the adequacy of that Arrhenius relationship, these points here. Okay, I'm going to go ahead and circle them, correspond to these hollow points here. Okay, so the red squares here in the design space correspond to the hollow points here. The filled in circles are actually values that we obtained. And as you'll note here, when I simultaneously plot my Arrhenius verification points as well as the actual observed data, I get a nice linear relationship. My R-squared adjusted is very high. Okay, so I don't really have a reason to believe that this model is inadequate. And if I didn't have these runs, if I didn't have these 4 runs here from the beginning in the model, I would have a much harder time assessing the validity of this relationship. For example, if I just had these 2 red filled in points here, how do I know that I wouldn't see something like this where I see a linear relationship and then it shoots up, or it plateaus here, and so on? By having had those extra verification runs to help assess this relationship, I know that a scenario like the one I just described is very improbable. So this was something that was quite useful that helped give us more information about the validity here. I'm now going to go ahead and actually fill in the rest of my design table. These red points here in bold are the Arrhenius verification points. The points in the last column are the points used to assess the predictive performance of the model outside of the design space. Okay, and now I'm going to go ahead and finish up the verification process. So, what I'm going to do is I'm going to add these verification runs. Before I do the data analysis, I'm going to add them to my design layout. Design Expert 9 has this nice feature where I can flag points as verification points. This means that the runs will not be used to build the model. They will be set aside, and later you can use these points when you do model confirmation. And notice that we do completely randomize. We do mix in the verification runs within the normal runs, within the DOE runs. And what we'll do after fitting the model is we'll go ahead and try to predict the response of the verification points, and we'll compare it to the actual values that we observed when we actually collected the data. I'm going to very briefly just take a look at the model fit. Everything that we expected to occur scientifically here occurred. Okay, we see that the water activity, the oxygen, and temperature all had a significant effect on the drug degradation rate. These results are not really shocking. Okay, and we would go ahead and use information from the ANOVA and the coefficients table to actually get predicted values of our to get predicted values. Okay, now I'm going to move on to the final confirmation stage here. As you can see here, I'm going back to this normality plot that I described way at the beginning of the webinar. What I'm going to do now is I'm going to plot the predicted values of the verification runs as well as the model building runs and test to see if all of the residuals are normally distributed. Once again, what you want to do is you want to see if all of these points lie along a straight line. We don't want any major deviations here. In this case, we see that there really aren't many issues here, nothing really to complain about. And similarly, you may remember this plot from the previous example, which is the residuals versus predicted. And this again is to test to make sure that the variance, in other words, the residual variance, is homogeneous, that it's uniform throughout the entire design space. That means at the points used to build the model, at future points, and so on. Once again, we don't see any obvious patterns. We don't see any megaphones. We don't see any kind of circular shapes where the variance is very low at the edges but very high in the center. Okay, so in other words, from here we see that, and finally we conclude by actually looking at all of the predicted values and all of the actual values and seeing how well these points fall along a straight line. Now remember, the key difference here is that these highlighted points were not used, so sorry, I'm not quite getting all of them, but these highlighted points were not used to build the model. These points were independent verification runs that were set aside, and later we used the model we fit with the other points to predict these 8 points. And as you notice, even though these points were not incorporated in the model building procedure, they still fall nicely along a straight line. So in other words, here we would conclude that a model is confirmed, and we can go ahead and use these results to, for example, try to predict the expiration date of the drug, now that we have a very good idea of the degradation rate of the drug. So to confirm the 3 strategies I talked about, the first one was to not confirm, which we in general don't recommend except in a very small number of cases. We talked about simple confirmation, which essentially involves performing confirmation runs after you've done the experiment. A single observation is better than no confirmation, but multiple confirmation runs are even better. And finally, we have this idea of concurrent confirmation, which we can do when, for example, the science tells us it's a good idea, and when we can't go back later, or it's too impractical to go back later and actually obtain more confirmation runs. In this drug degradation example, we would have had to have waited months if we went back to do confirmation after we fit the model, which would have essentially doubled the time it took to do the experiment. But with concurrent confirmation, we were able to do it fairly quickly. Okay, so I'm going to go ahead and conclude this. This section here is quite short. Okay, but I'm going to go ahead and conclude just with some practical tips and tricks that might be able to help you as you go forward and try to apply this stuff in your future work. Common pitfall, something you definitely don't want to be doing, but something that we see that occurs every once in a while, is that you use the R-squared, which is the coefficient of determination, as a way of confirming your model. Do not do this under any circumstances. Mathematically, the R-squared cannot decrease when adding terms to a model. Even if you, for example, just make up random data, put it in the design matrix, and fit the model that includes the bogus data, your R-squared will still suggest that that bogus data has a positive impact on the model. Completely false. Do not, in general, try to avoid this statistic as much as possible. It will always point to using a larger model, which will make you more likely to overfit and will give you a model that performs very poor in the future. Also, note that some processes are just very hard to measure. Sometimes you have these processes where the response is unwieldy. It's kind of all over the place, And so even great models can have low R squared. I was talking to a friend of mine who's in finance, and he mentioned to me that a lot of times their models will have R squareds that are on the order of 0.5%, 1%, or maybe 2%, which would be considered extremely high. And yet they use those models all day and every day. So even great models can have low R squared. It's just you might be dealing with a process that's very difficult to measure. If you do want to go down the route of R squared, you'll want to look at this predicted R squared, which is reported with Design Expert 9. This is a much better option, as it actually does give you some degree of model confirmation. Okay, next. Always use your subject matter knowledge when confirming models. If something smells funny to you, it's probably because it smells funny. If you fit a model and it doesn't suggest that it should work, if it goes against all intuition, you really need to go back and reconsider your model. Okay, if you do perform model confirmation and it confirms the model, it'll tell you if it's adequate or not, but it won't tell you why. And these below here are kind of two classic examples. The first example here is the Internet Explorer market share versus the homicide rate, the murder rate in the United States. As you'll notice, in 2006, the Internet Explorer had something like 80% of the total market share among Internet browsers. And you'll see that the homicide rate was fairly high. In 2011, the homicide rate and the Internet Explorer usage rate both dropped. So if you were to go ahead and fit a model that used Internet Explorer market share as a way of predicting the murder rate in the United States, you would see that, wow, if I just know what the Internet Explorer market share is, I can predict the murder rate. So that means if Microsoft goes away entirely, if they finally shut down Internet Explorer, the homicide rate in the US will fall much lower. False. Okay, why? You might get a great model, but subject matter knowledge, which in this case is really just common sense, will tell you that these two have nothing to do with each other. This was just a random occurrence. This pattern just occurred by chance, and because you have that information, because you know that these two quantities are independent of one another, intuitively speaking, you would know that even if a model looked good, you would never believe it. Because if Microsoft shuts down Internet Explorer tomorrow, the homicide rate is not going to zero. Here's another kind of classic example, the Greek debt crisis. It turns out that the number of Facebook users increased tremendously at about the same time as did the 10-year, as the yield on a 10-year government bond, a Greek bond. So if you were to fit a model that used the number of active Facebook users to predict Greece's debt levels, you might come to the conclusion that all Greece needs to do is shut down Facebook and all of its problems will go away. False. Because anybody that has even basic, that knows basic economic theory can tell you that these two actually have nothing to do with each other. And that if you looked at the relationship going forward, you might see something like this. Okay? Always use subject matter knowledge, because even though sometimes if something really goes against your intuition, you need to investigate it. That doesn't mean you need to throw away the result and redo everything. You just need to take a second look and give it some thought. When in doubt, okay, when you're in doubt and you have several models that appear to be adequate, you'll probably want to go with a model that in general is smaller than one that tends to be larger. Now this is, as a disclaimer, this is generally true, but definitely not always. Okay, and here I just give an example of a model that's underfit. Okay, so if I have any confirmation runs here, I'll notice that the predicted value is very far from the confirmation run. Here I have a model that's overfit, that I'm just fitting noise. All I need to do is delete this point, this point and maybe these 2 points here, and I'll get a curve that's quite different from this curve. And finally, I get in the middle here, I have kind of the strategy I want to follow. Okay, and that's to get a nice general relationship that can be applied in the future. Finally, you should always focus on confirmation techniques that use external data. You may have heard of techniques like cross-validation, data splitting, and so on. You always want to confirm your model whenever possible by using fresh external data, unbiased independent data. Predicted R-squared and the PRESS statistic, these are both computed by Design Expert 9, will give you some information about how well a model will predict future responses, and generally will give you evidence of underfitting or overfitting. It's just an additional tool you can use. Okay? Again, just to reiterate a little bit, you should use confirmation runs to verify the predicted responses at locations of interest in the design space, for example, at points that minimize or maximize the response. And future versions of the Design Expert software will likely include many techniques, will include new techniques for doing out-of-sample confirmation. Last slide of content is how to deal with a situation where you have blocks in your design. Okay? If possible, you want to perform the confirmation runs at many different blocks, assuming that you can actually go back and repeat at the same blocks. If you're, for example, if you're just going to repeat at a machine, that's no problem. But for example, the third point here is if a block is actually something like a year, well, obviously I can't go back in time and repeat the experiment in a previous year. So what you want to do is if you have 5 confirmation runs to divide up, you want to divide them up across the different blocks so that you can kind of get those block averages those block effects to average out. If you can only perform one confirmation run, go and look at the ANOVA report and the summary report and choose the block with the effect who's closest to 0. This should actually probably say not the lowest effect, but it should say the lowest absolute effect. So in other words, the effect that's closest to 0. Do the confirmation run at that block because it'll have the least effect on the response. And again, just to conclude, not much can be done if a block's not repeatable. You'll just have to go with what you can do at that point and hope for the best. Okay, so as I conclude, how can you get more help? Let's say that this topic is of interest to you and you want more resources. www.staties.com has a number of publications posted that we've collected over many, many years. Lots of helpful publications that can help you in future experimentation. If you use the Design Expert 9 software, it's loaded with screen tips, context-sensitive help, and it also has a very extensive help system. You can also look within Design Expert, you can also view most of the reports within annotated mode, which means there will be paragraphs below the output that'll actually kind of give you some information about what's going on in case if you just can't really, in case if you need a little hint. You can go to this forum, which is the forum.staties.com. This forum is currently read-only, but there are tons of questions that have been posted, and there's also many contributions there. So you can go browse around and see if maybe any of the topics are of interest to you. You can email stathelp@staties.com. There are a number of consultants that may answer your questions, and we usually are able to answer you fairly quickly. And finally, you can also go ahead and call this number here during normal business hours and ask for statistical help. And just maybe as a reminder, you can also, at this website, staties.com, you can get a free 45-day trial of the Design Expert software, so you can actually go ahead and try out some of these new techniques and practice them. If you don't opt out, we also have a tri-annual Stat Teaser newsletter, and we also have a bi-monthly Design of Experiments FAQ alert. This FAQ alert is particularly useful because it includes lots of FAQs, meaning a lot of the interesting questions that people ask us. We'll usually post the question and the response, and people often find this to be very useful. So you can go to this website here, and recall, you don't have to frantically write all this down because this presentation is already posted at the Staties website. Okay? And finally, if you're looking for some interesting applications of statistics, some that may not necessarily have to do with design of experiments, you can go ahead and go to this www.statsmadeeasy.net website, which is run by Mark Anderson of Staties, and see if you find any interesting articles there that may help you in the future. So I want to thank all of you for joining us. I hope that you have learned something. I hope that this webinar may have given you some ideas for future work that you'll do. And as one final reminder, if you're going to write something down, this is the email. This is the website where you can actually find this presentation. And in approximately 1 week, this and a voiceover version of this presentation will also be posted in case if there's something you may have missed the first time and you want to go back and take a look at. And the very last page is just a number of technical references. So journal publications, textbooks, and so on. These are much more advanced resources, but all of them have something to do with what I talked about in this webinar. So I really wish you all the best of luck. I wish you all a great morning, great afternoon, or great evening, depending on where you are. Here it is approximately 9:15 p.m. We wish you all the best, and of course, we encourage you to use the resources that we included at the end of this talk. And once again, we'd like to thank you for joining us and hope to see you in future events. Bye-bye now.